Swayam Prabha. Digital India. Educated India.
So, hello everyone, this is Shreya here. So, we heard Yogesh sir talking about IoT and its applications. So, whenever we come up with any such idea and development we have in our mind, it's very important to do the testing at several stages so that we have our setup really efficient. This is where simulators come into picture. So today we'll be talking about simulators, their usage and types, how you will know which simulator you have to use. We'll dig a little more into NS3, and Suman will be showing you some multi-drone systems, and we both will give you a demo about the usage of the same. So what are simulators? Basically, simulators are machines or devices that imitates the behavior or properties of your physical systems in a virtual environment. So suppose you have physical system like sensors, actuators. You may have one or many of them coupled together, which are into communication using some API socket APIs in a virtual environment. And then you have your application or code setup, which you run as a simulation, and then you do the analysis on your output using some graphs. You have various types of simulators: network simulators, physical simulators. Network simulators are basically when you're trying to simulate your network stack, which is basically when you consider your OSI model. So you have Puja, which comes under Contiki OS, and network simulator, which you can use as network simulators. When it comes to physical simulators, it's basically when you're trying to simulate any of your hardware, like suppose vehicles or drones, in which you can use Sumo or Gazebo as simulator. Then you have two varieties: simulators versus emulators. How you would know which you should go for and what it actually is. So, like we mentioned, simulators are basically you are trying to have your physical system imitation in a virtual environment. And emulator is something where you have a physical setup. Suppose you know how many cores you should have, what CPU you should have, and then you are trying to have emulation of your suppose distributed network setup. That is where emulators come into picture, and some of them examples are Mininet and Maxinet. Moving forward, why do we actually need to use simulators? So basically, when it comes to IoT, network plays a really vital role. And to know in what environment, how your setup is actually working, what's the connectivity, whether your system is stable or not, and how it actually behaves, it's very important to do the simulation before actually having your hardware set up, which may be really costly to have. So that at any stage, whenever you feel like making any changes, you can do before having a normal test bed. So simulation can happen either at any one of the layers, or maybe you may have to do the simulation at all of these layers. So suppose just in case you are trying to simulate your physical layer, that means you are trying to test whether your radio transmission is happening properly or not, what channels you should use, which channels behave more efficient. That is when you would go for the physical layer simulation. When it comes to data link layer simulation, is when you're trying to know the efficiency, the error detection of your system. That is when you go for the data link layer simulation, basically the CRC, CSMA, CACD checks. When it comes to network layer, it's basically you get to know what is the packet drop and what's the packet received, and which protocol you should go for, whether IPv4, IPv6. That is when you try to simulate your network layer. When it comes to transport layer, it's very important to get to know the reassembly of your data segment. Like just in case you are trying to send some 5,000 as an input, it shouldn't go 2,000 first and 5,000 later. So it's very important to test your transport layer there. Application layer, I believe you might have read about some of the application layer protocols like CoAP, MQTT, which are basically comes under IoT application layer protocols. So when you have to test which protocol would suit best for you, that is when you do the application layer simulation. Okay, so how would you know? There are so many simulators available. Some are open source, and some you really need to buy on. So how would you know which simulator you should actually choose for your development? So there's a simulator called Puja which comes under Quantiki OS. So just in case you are trying to simulate a very power constrained network, some wireless sensor networks, basically working on Zigbee 802.15.4, and that is when you should actually choose Puja. When it comes to network layer, you will see this is basically a Quantiki network stack. So at network layer, you will see we have something called micro IP setup. So when we don't want an entire stack of IP, so that it won't take much load on our system, and it should basically work with microcontroller 8-bit, 16-bit. That is when Puja plays a very important role, and it will the best choice to go for. It's very important to be very aware of RPL, which is routing protocol for low power lossy networks, and knowledge of C is very important to work with Puja simulator. But when it comes to NS3, it is not only limited to power constrained networks, but you can work with several other protocols as well, whether it is Wi-Fi, LTE, flying ad hoc network, or mobile ad hoc network. All of them can be simulated using NS3. And also, just in case you are trying to simulate a drone or a 3D model, that as well can be done using NS3. Knowledge of C++ and Python is really important for NS3. So some of the Python bindings are available in NS3, but C++ is the major language that you have to work on. When it comes to emulator, like I said, Mininet is very useful for distributed network simulation. And if you have a Wi-Fi setup that you are trying to simulate, so suppose you have some n number of switches, nodes, and you are trying to have a link between them, you want to check the network performance between the setup, that is when you can use your emulator as Mininet or Maxinet. Any questions so far? All right. So we'll dig a little bit deeper to network simulator NS3, which is basically a discrete event network simulator. It is called discrete event network simulator because we have some set of events being scheduled, and all these events are being called using callback functions. And once all of the events are being called, our simulation gets over. So there are a few things that come under network simulator. Model development. So suppose you have some n number of nodes and you aren't aware where exactly they are being placed, and they are randomly placed. So that is when NS3 provides something called random mobility model. And then we have constant position mobility model when you actually know at which XYZ coordinates your nodes actually are being placed. That is when you use the constant position mobility model. Other thing is when you want to know the link performance parameters of your setup, whether it is data rate, latency, packet loss, throughput, lot of things can be examined using NS3. It's not just the UI that is being available with NS3, but in case you want to tell the kind of protocol you are using, the session you are using, number of nodes that you have, that time you can use the command prompt to simulate your environment. For performance analysis, there are a lot of modules available. We will be taking a look into NetAnim, but we have Wireshark, packet capture, flow metrics, everything available inside NS3 to test your network performance. For the analysis of your performance, just in case you want to analyze what is the throughput you are getting at certain period of time, you can do that plotting using GNU plot being provided by NS3. I've provided a link here just in case you want to go through the documentation of NS3. Okay, so since NS3 is all about mostly about coding, so it's very important to understand the software organization of NS3. So it starts with the core where you give your logs or the variables that you are trying to use. All the events are being scheduled. Everything happens inside the core. When you come to network layer, that is when all the packet capture information lies in the network layer. When you come to internet is where you have your nodes and you are trying to have an internet connection in them. So you provide the address and particular port that you are trying to connect using basically these socket APIs. Mobility, I already mentioned, you have starting, random, and constant position mobility model based on the type of nodes that you are using. And you have lot of helper basically are wrappers that are being provided in C++ by NS3. So suppose you are using LT stack, you will be using LT helper that will be provided with all the stack information, and you can go on with the development. And the test layer is the one which has the main application code being written by you, which you will testing at the test layer. On the right hand side, you will see the flow diagram of an S3. So suppose you have two nodes and there should be a connection between the two nodes. So channel is the one which provides a logical pathway to have connection between these two nodes. Then you have a network device, basically a network setup on your nodes where you provide the IP addresses and port of at which you are trying to have the connection. Protocol stack is basically whatever protocol you are using, whether it is LTE, Wi-Fi. So you should have a stack on your node, and application, like I mentioned, is the code which you will be testing. The sockets that we basically use here are Berkeley sockets, so it's pretty easy to use. Okay, so here, this is a use case, V2X use case that I was working on. So what I am actually trying to do here is I have some n number of vehicles passing by, and they are passing through some two LTE 4G towers. So what I'm trying to do here is I'm trying to calculate the network performance parameters. Network performance parameters as in what is the latency, bandwidth of the data that is being transmitted, throughput, jitter. So whatever values you want to monitor, you can monitor here. So I give it to NS3, and this is the visualization that I see. And I'll give you a demo now.
Yes, so I'll give you a short demo here.
Is it audible now?
Yes, ma'am.
About how I made use of NS3 to do LTE simulation. I am using NS3 version 3.27, which suits well with LTE. In case you are working with the latest IoT development and related protocols, it would be better you use the latest version. You can follow the following steps for the same. The next thing that I'll be using is Sumo, which is urban mobility simulator, basically for traffic modeling, vehicle connectivity. So in case you are looking for some vehicle simulation, it would be better if you go with Sumo. You can follow these steps for Sumo installation. So I'll just show you how to do that. You can do Sumo simulation manually as well by giving XML files of your nodes, edges, and the connection between them, and give some commands to get it run. We will be using OSM web wizard here to get the UI of Sumo. Yes, so you can select whatever location you are looking for. We'll select Bangalore for now. It would be better to select a particular area so that it doesn't take much time to load. Left hand traffic for India. For other countries you may need right hand traffic, so you can just deselect it. And yes, for vehicles, whatever vehicles you are looking for, trucks, bus, pedestrians, so we'll go with this for now and we'll generate the scenario. Yes, so we'll start the simulation. We'll increase some delay. Yeah. So I hope you are able to see the vehicles moving on in the particular lane. These red lines that you see are the traffic signals. You can change the traffic signals, lights, and you can lot of things that you can do here as per your wish. Yeah, so for now you will stop the simulation. Yeah, a few things to keep in mind. When you are running a file inside NS3, it should be inside Scratch folder, because Scratch folders has all the required permissions and binaries to get your code run. Also, WAF is a kind of build model like you have make in C. The same way, it's a Python build model used for running NS3 files. So I have my file inside Scratch. So if you see, basically I'm trying to get the network performance parameters for my specific number of LTE towers and the vehicles moving around them. We will be using NetEnim here to see the simulation. There are a lot of things that you can do, like if you want to have a packet capture or ASCII trace, or you want to use Wireshark, you can use all of them inside NS3. So the simulation has started and the transmission is happening between the towers and now towers to vehicle. The circles represent the amount of traffic that is present. So you can go to stats to see the IP addresses of the towers and vehicles among which transmission has happened. Also, you can check the network performance parameters here as well. Yes, so for each transmission that has happened, Flow Monitor will provide flow IDs and you will be able to see the data here. Okay, we'll take a short look into the code now. Yes, so Flow Monitor is basically a model which makes use of probes to get the network performance parameters. So NS3 gives this leverage to use Flow Monitor here. So this is the extra code that you need to write to get the whatever values you are looking for. You can also use GNU plot to get the plotting. Suppose you want to know the throughput for particular timestamp, you can have a GNU plot for that. So like I was talking about the mobility model, if you see, I am using constant position mobility model for my cell towers and random mobility model for my UE nodes, user equipments. Yes, so this is some extra code that you need to write to get the images in your NS3. As if you don't want, it will just give a circle there. And yes, that's all. In case you have any doubt, you can always ask. Yeah, thank you.
Yes, so that's all from my side. Any questions anybody has?
Shreya, just wanted to confirm that NS3 is open source, right?
Yes, it is. Yeah.
And these maps and other things can be got even with the free license.
Yes, we do get
Okay.
it.
Anybody else has questions for Shreya?
All right, then we'll move towards the multi-drone systems.
Okay.
So Shreya or Suman, can either of you also share the link to the GitHub page having all these details? I've just made it a public repository, so students can try out all these instructions by themselves as well.
Suman, you can start now.
Okay, sure. Thank you, Shreya. So now we'll go through this multi-drone systems. So this multi-drone system, they are basically a system. They consist of this multiple drones, and they can cooperate and communicate with each other in order to accomplish certain tasks. So as of now, the single drone is very, very less capable as an entity. And only if we have multi drones and it scales up, then only we can achieve practical tasks. So the impact of the problem is increased only when we scale the number of drones. So there are various applications of multi-drone system. The first is military missions, let's say battlefield surveillance or search and rescue. Then second is searching for survivors in the disaster hit areas. Next, as we have seen, it's trending now, like Amazon and other delivery apps, they are using drones for delivery of payload. And recently we have seen drones emerging in the entertainment industry as well, in the form of drone light shows. And as Professor Yogesh has talked about, we use drones in context of smart cities as well. So the major complexity, it lies in the coordinated movement of these drones and how they interact and communicate with each other. So next we will look at why do we actually need the simulation of multi-UAVs. Yeah. So as we know that practical evaluation of any UAV network, that requires a lot of money to build the experiment environment. So let's just take one example of UAV fleet deployment in a city for package delivery. So the first constraint comes in the form of resources. So we'll have to buy UAVs, then we'll have to have the network devices, then the flight controllers and all of these things. Second comes the operational constraints. So let's say we want to test our drone in field conditions, then it's not every time that we get the factory floor permissions and all. And let's say if it has to go in the open environment, then we'll have to have all those access. So operational constraints do come into play while having the multi-drone experiments. Next come the scalability challenges. So if we want to scale, let's say we can buy 1 to 10, let's say 50 drones also, but if we want to scale on a city level, then we will have to deploy, let's say, not hundreds, then 1,000 drones. So devices may not be available in specific quantities then. So this is a major challenge, and simulations do help over here. The next one is that it is always a safe risk compared to the hardware failure. The next is whenever you are going to simulate and we know the system is going to behave in a certain way, then we gain a certain level of confidence. So, and in order to investigate this time sensitivity of the multi-UAV network, so the UAV's mobility, it has to be precisely evaluated in the long term. So in order to address all these challenges, we have several simulation environments gaining traction in the research community, some of them being ROS, AirSim, Gazebo, and MATLAB as well. So moving on. we will see the component that is required in an UAV simulation. So in a drone, the thing is the physical design of the drone, as to what is the weight of the drone and how many rotors it is, quad rotor or hexa rotor. So we need to know the physical design of this drone that we are going to simulate. Second, we will have to get the sensors. So the different sensors are there, let's say LiDAR or camera, then accelerometer. So all these sensors should be there, which are going to take the inputs from the environment. Next is the actuator. So the inputs that we get from sensor, and like what is the action that we are going to take with those inputs. So we will need to have different actuators, the common one being the motors. Now we will definitely have one energy source, that is the battery or gasoline. Then we'll have the controllers. Then we also need to have the communication or networking that is required in the multi UAV simulation, or if not multi UAV also, this single drone needs to communicate to its base station, in which the communication comes into play. Next, we have the onboard compute. So let's say the camera is taking in the video feed and it has to analyze and take decisions based on that. So the onboard compute also comes into picture. So the first 5, the ones which are in green, can be simulated using ROS and Gazebo, and the next 2 are out of scope for these 2. So we can always integrate ROS with other features, like let's say NS3, and we can have the communication going on. But these 2 are out of scope with just the perspective of ROS. So moving on, we'll understand what ROS is. So let's say we have a robot, and so what is a robot basically? So it is a system, it perceives the environment, that is its surrounding, using the sensors, and then it takes the decision based on the state of the environment using some computation or algorithm, and it is able to execute these instructions using the actuators. So ROS is basically an open source meta operating system for your robot, and it is not an operating system because it's not just about process management and scheduling. Rather, it provides a structured communication layer above the host operating system. So it provides the services that we would expect from an operating system, including the hardware abstraction, low-level device control, implementation of this common used functionality, the message passing between the processes, that is the inter-process communication, and different package managements. So it also provides tools and libraries and for obtaining, building, writing, and running the code across the multiple computers. So ROS has a distributed nature. Next, it also allows, sure. So next we have Gazebo Simulator. So Gazebo Simulator, it is a tool which is already included in the ROS operating system. So this basically provides the tools. It is basically allows us to simulate the 3D rigid body dynamics, which in our case would mean the multi-body robots like robotic arms, or let's say any drone, or even the obstacles like trees, buildings, all those we can model over here. Next, it is also used to simulate different sensors, which can include the noise as well, and we can add these objects inside the simulation. So it provides a ROS interface so that we can use it with ROS, and Gazebo is extensible with plugins, which means that we can write the code to customize the behavior of the different components which is inside this Gazebo world. And Gazebo world is nothing but it is the environment in which we want the robots to move around, and we want to read the behavior of those entities. So this simulation tool, it is already installed in ROS. Yes, so moving on, we'll understand the case study of a drone flying to a waypoint for package delivery, let's say, or for any other purposes. So what is the workflow of that? So the first thing that comes is the drone structure, the physical design that we had. So we need to specify the weight and the position of the sensors on the drone, and the position of the motors and every other thing, the physical structure. So in this URDF file, which is which defines the drone structure, this has 3 categories. It defines the inertial frame, about the mass and about the weight and all those things. And then it has the visual frame as to how should the robot appear. Like you can set the color of the wings or set the transparency and all those things. The third one is the collision frame. So it will say that in this area, if this particular drone collides with a certain flag post on a pathway, then it has to collide, which means the drone is going to fall down. So this is the structure that we are going to define, and then we will be launching that. So this, once the drone is launched, then we are going to launch the gazebo world. So this is a world which has obstacles. So obstacles are nothing but buildings, trees, pathways, so all these things. So these are defined in the gazebo world. So first we launch the ROS environment and the gazebo world. So the interaction between them is such that all these sensors and actuators, everything, so they are started as a different process. So let's say we have a sensor, the position sensor, then it reads the position of that of the drone at a particular position, and it sends to the controller, to the position controller. The publisher is sending the position to the position controller, and this position controller will determine as to what the speed of the different motors should be in order to reach to that position in that particular time range. So that is being fed to the motors, and the odometry sensor reads the position of the drone. So that is being subscribed by the waypoint subscriber. So all these nodes, the odometry sensor, the motors, and the position controllers, they are attached to the gazebo server. And gazebo is nothing but simulation of how the real world will look like if we run it in a real environment. So this basically does that. And gazebo has 2 components. One is the GUI and one is the server. So GUI is optional and server has to be there if we want to simulate our experiment. So gazebo is the environment, and if at all we want to integrate the hardware parts, then we always have the ROS drivers, and gazebo can be replaced with the hardware. So yeah, now we will go to the demo. So first we will be seeing the demo in which we have multi drones simulated. So we go to the GitHub repo and then the physical simulators folder. Here we can find the steps to install ROS. Now the first requirement is Ubuntu OS. We have different versions of ROS which are compatible with different OS versions. For Ubuntu 18.04, we have ROS Melodic. And the steps have been taken from this website. Since I already have ROS set up on my system, I'll skip these steps. Now, in order to check if we have set up ROS, we run these commands. So this particular command, it sources the ROS workspace environment, and it tells ROS as to which packages should the applications use inside this workspace. Now this is the output which we should be expecting if we have ROS installed successfully on our system. So this Melodic is the ROS distro which is installed, and it can vary depending on what version of ROS you are using and what Ubuntu version you have used. So if it is Ubuntu 20.04, we have ROS Noetic for that, and similarly for the other versions of Ubuntu, we have Kinetic and Melodic. Right. So now that I know that I have ROS successfully set up on my system, I can go ahead with this project. So the first step after that setup is to create a workspace and use it for your project. So these steps from line number 31 to 35, we will be skipping these because it has already been done for this project, and you can directly proceed to the next section for downloading the files. However, if at all you create a new project and you want to build it, we do that using the command catkin make. And if it is the very first build, we pass this parameter which specifies which version of Python we are using, and for subsequent builds we just pass the command catkin make. Now once we have already downloaded the gazebo simulation source files, we will have to install this package called ROS Melodic Octomap. So this is basically the message type that is being passed using the waypoint publisher nodes, and this has the data type of the position and the orientation of the drones. Now once we unzip this gazebo simulation file, we will see that the folder structure is as this: ACM School IoT 2021 and gazebo simulation. So if we go to this gazebo simulation folder, we will see that there are three building blocks: SRC, build, and devel. So SRC is basically where we work and we create the code. And once we issue the command catkin make, so that creates the build folder in which ROS builds the packages from the source space. And once all the binaries and target files have been created, they are kept inside this devel folder. Hence, whenever we create a new terminal and we want to set up the project workspace specific environment, we always use devel setup.bash for sourcing it. So let's go ahead and get started with the project. So the first thing I do is I will always source this devel setup.bash in each terminal, and I'll start the ROS core, which is starting the ROS master. So this has started the ROS master, and this is the logging file output location. And this is the ROS distro as melodic and the ROS version. So we see that this has already started a new process, which is the ROS core, and the ROS master URI, it always runs on port number 11311. And this ROS out is used for logging. So the next step, what we do is we will go ahead and start the gazebo world. So ROS launch is a tool which is used to launch multiple nodes or processes. And if ROS master is not already running, this will also start the ROS master in addition to launching the nodes which are required by the project. Rotor's gazebo is the package name, and gazebo launch.launch is the launch file in which I have written which world it should launch. Like the world should contain which buildings, the design of the buildings, and the pathways, the trees, the lamp post, and the location for all of these objects. So once I launch this gazebo world, it will start this gazebo. Yeah, and we see that this is using the ROS distro as melodic, and this is starting up two processes basically. One is the gazebo, that is gazebo server, and one is the gazebo GUI, that is the gazebo client. So, and this will subscribe to the ROS master URI, which is running on 11311, as we had already seen the location of ROS master. So yeah, if we look at the gazebo world, this is the origin and this is the X, Y, and Z axis respectively. Now these are all the houses which have been defined in the world file, which is being launched using this gazebo launch file. So this is the base station, and these are the different houses from where the drones will pick up packages and deliver to these houses. So let's go ahead and start launch the different drones as well. So as we can see, even this is subscribing to that particular ROS master. So all of these nodes with the processes which are starting, they all have to subscribe to this ROS master. So yeah, as we can see that it has started different processes for all the controller nodes and joint publisher, state publisher nodes. So this is Iris, which is the type of the quadcopter which I have launched. There are different types of quadcopter in the project that you can explore and try. So Iris 2, 3 and 4. So I have launched 4 drones in this. And as we can see, it has already come up in the gazebo world. So these drones, they have to pick up packages from the base station and they have to deliver to all these houses. And each drone has been mapped to which house it has to go to. So let's try and do that. So the first thing we'll do is we'll start the publisher node, which will read the position of all the drones so that we know that they are going to the correct locations. Yeah. So this is 63, 65, 61. So it is publishing the position of all these different drones, all the 4 drones. Now we'll start the publisher node. So this publisher node is a node which is sending messages to all these drones regarding the waypoint as to where it has to go. So now we see that all the drones have taken off towards their specific location. So these 2 drones are heading towards this direction. So this has successfully landed at this house entrance. Even this has successfully landed now. Now we'll go and check this particular drone. So even this has done. And if we go and check for this drone, so even this has landed to its location. So as we see that the process has completed, so this is how we design simulations in Gazebo, and we see we analyze the behavior of all these components. Yeah, so now that we have seen this, how the multi-drone simulation happens, we'll just take a look at what happens if the waypoints are not given properly. So let's see what happens exactly over there. Yeah. So the drone takes off, but then it sees that there is a lamppost in its way. So it just collides and it falls down as it would happen in a real world scenario. So we can justify that, yes, Gazebo is the correct simulation environment in which typically depicts all the physics theories that are out there. So yeah, any questions, please feel free to ask.
Yeah, any questions from the participants?
Will this ROS is supported only in Ubuntu?
Yes, so ROS is supported only on Ubuntu, correct? I mean, in any Linux version, not necessarily Ubuntu, but Linux should be there.
Many of you were always looking for what can I do without hardware. So today you got an excellent example of what you can do without hardware. So I presume Gazebo is also open source, right? Suman,
right,
like
ma'am.
NS3, yeah. And this code that you write for the drones delivery can be sort of almost directly ported onto a real system.
Yes, so we'll have to make certain changes, but yeah, the algorithms and the control functions that we write, that can directly be ported.
Okay. Any questions or points that you would like to discuss or get to know? Please do
Ma'am,
ask.
so the communication between different drones is not simulated in Gazebo, right?
Right. So the communication between the drones, if it has to go to a different communication layer itself, then we'll have to integrate ROS with NS3. So that will serve that purpose.
So my question was that only how do we integrate NS2 or NS3 with this Gazebo servers, and if we want to in real time test the communication as well?
So we'll have then right now what we saw is we saw one demo of NS3 with Sumo and one with ROS with Gazebo. So basically for your application, I guess we'll have to have ROS plus Gazebo plus NS3. So that will be the actual architecture for your problem statement, I guess.
Now we use camera as a sensor to validate the drone's functionality, right? So does Gazebo also support other forms of sensors? Like, I mean, a drone can, one of the sensors is camera, so drone can also carry a GPS. Other
Correct,
kind of
correct.
sensor,
So
right?
those
So can we also simulate that using Gazebo? Is it possible?
right, GPS can be simulated using Gazebo.
And is it a near real-time experience? As in, is it foolproof?
Right,
This
right.
kind
Yes,
of
yes.
validation?
So the reason Gazebo is very much in the research community is that it provides the real-time results, as we would see in the practical experiments.
So let's say you want to today create a small map. You do a GIS survey, take a map of a place, and and you want to develop an application to drop packages in each house only in that community. So this Gazebo, can it simulate the entire GIS map of the real-time map? Is it possible?
Right. So first we'll have to have the exact configuration in this world file about that, about the society or the community. And then we'll have to feed in the drones as to where it has to go and what obstacles will it see in the pathways, like these lamp posts and also they have to be I mean, they have to be configured properly in the world file. So yes, that is why we use Gazebo as a simulation. So it is helpful in those scenarios.
In terms of programming these drones, what language is suitable for programming drones in Gazebo?
So it is multilingual. However, Python is very famous right now, but you can always use C++ as well. And I guess recently they have started supporting Java also. So you can take a look at that. But right now, Python and C++ are very popular.
Thank you.